Good morning and good afternoon, everyone. I am Laith Tamimi, President of Semi-Europe, and today I have the great pleasure to welcome you to today's Future Fab webinar in collaboration with Seagate, Flexiton, and Linceus. Title of the webinar, Adopting AI-Driven Smart Manufacturing Technologies. What will the future of wafer fabrication look like with innovative AI-driven technologies paving the way for significant improvements in efficiency, quality, and on-time delivery, whilst driving down costs? The webinar will present two disruptive deep tech companies, Flexiton and Linceus AI, and our speakers will introduce their cutting-edge technologies and discuss the efficiency gains achieved from deploying these solutions into a live production environment. We will learn more about how real-time performance monitoring can dramatically speed up and increase the accuracy of fault detection, real case studies presented by Linceus, and how Linceus's technology has already enabled value in deployment on deep trench etch and quality predictions at a tier 1 automotive supplier, as well as how Linceus enables reduced metrology sampling and faster time to defect faults in a photolithography use case. A special thanks to our colleague, Mark De Silva, Senior Director, Smart Manufacturing, for moderating the Q&A live session after the presentations. Please be ready with your questions to our speakers and don't miss this great opportunity to learn more about Future Fab innovative technologies. We wish you a great webinar. Thank you for your participation.
Hello, everyone. Welcome to this presentation between Flexiton and Seagate. My name is Jamie, and I'm the CEO and co-founder of Flexiton. I'm really excited to talk to you today about improving wafer fab capacity by applying advanced production scheduling to the photolithography area in a Seagate technology wafer fab. On the agenda today, I will give you an overview of Flexiton and our approach to solve the wafer fab scheduling problem. Then I'll hand over to Tina O'Donnell, Global Wafer Systems Manager at Seagate, who will take you through why Seagate needed an advanced scheduling solution, the particular application in photolithography, and the results seen in that area of the fab, and also what's coming next. So firstly, I'm going to introduce Flexiton and our advanced scheduling technology. So firstly, some background on Flexiton. We are a deep technology company focused on helping wafer fabs improve production efficiency by solving their scheduling problem. We are very fortunate to have over 40 world-class engineers and scientists in our team who are extremely passionate about solving scheduling problems. They have published over 400 academic papers between them. Our core product is a Flexiton scheduler. Our scheduler is designed to deliver fab-wide optimized schedules quickly. It is capable of handling all of the constraints you would find in a fab and is built on the latest modern cloud-native technologies. To solve this complex scheduling problem, we use some of the latest advancements in mathematics. Our solution combines mathematical optimization, heuristic search, and decomposition methods. And using the power of cloud computing, we are able to calculate an optimized schedule within a few minutes. At the core of our solution is a mixed integer linear programming approach. This is an optimization-based approach where we can describe the objective of the fab, and the optimizer will decide the optimal allocation of lots to tools, subject to all of the physical constraints in the fab. The wafer fab scheduling problem is extremely complicated. Using this approach, we've managed to create near optimal schedules within 4 minutes. Historically, many fabs have used either a dispatcher or a heuristic-based scheduler, or some combination of the two. Now, these systems use a rules-based approach to scheduling. However, these rules can often lead to inefficient decision-making. Take, for example, the rule described on this slide. The rule is a typical rule which can be found at a batch tool. It refers to dispatching wafers, and it says, wait until a minimum batch size of 3 is formed, unless more than 30 minutes have passed. While this rule may lead to good decisions sometimes, it will also lead to poor decisions on other occasions. In addition, a rules-based approach typically tries to optimize one small part of the process and doesn't consider the bigger picture. In contrast, our optimization-based approach works purely from the objective you describe for the fab. Once that objective is described, it will consistently provide near optimal decisions, no matter what the dynamic is in the fab. Now, the solution contains 3 different levels of optimization aimed at optimizing the entire fab. At level 1 is our local toolset optimizer. This purely looks at the WIP in front of or arriving at a toolset and optimizes toolset-specific KPIs. Level 2 is our global fab optimization. This optimizes the flow of WIP globally around the fab and ensures optimized supply of WIP to individual toolsets. Finally, at level 3 is our release decisions optimization. This optimizes when to release WIP into the fab in the first place. The optimization is extremely fast with an end-to-end time of 4 minutes, and the system has been designed to integrate with the fab's existing MES and dispatch system. Now, I'd like to explain in a little bit more detail how 2 of these components interact. The purpose of the global fab optimization is to optimize the flow of WIP globally around the fab and ensure optimized supply of WIP to individual toolsets. It does this by scheduling a long time horizon, say 24 hours, and predicts where bottlenecks are likely to arise. When bottlenecks are predicted, wafers likely to queue at a bottleneck are reprioritized upstream in order to alleviate those bottlenecks. This is communicated to the toolset scheduler, since it seeks to optimize the toolset KPIs with guidance from the global scheduler. To explain this in more detail, I'm going to show you how we look at a fab from a scheduling point of view and why these components are needed. Now, firstly, I want to explain what you're going to see on the following slides. I'm going to show you a heat map, which represents how dynamic a typical fab can be. In this heat map, each row will represent one toolset in the fab. Each cell will then represent how bottlenecked that toolset was on that particular day. For example, as you can see here, the red cell means that toolset A on day 2 caused a lot of queue times to the wafers that arrived in front of it. It was a bottleneck on day 2. The green cell over on day 4, however, shows how on that day, the same toolset A, caused very little queue time on that day. On day 4, it was not bottleneck. So here you can see the heat map of a typical fab over a period of a couple of months. Remember, each row represents a toolset and each cell represents one day. Let's just take a moment to take in what you can see here on the slide. Firstly, you can see that some of the toolsets only have green cells, whereas some of the toolsets can vary from green to red within this time frame. What's immediately obvious is just how dynamic a fab can be. This is largely caused by the nature of wafer fabrication, in particular the multiple reentrancy and the variation in tool availability. The ideal role of the scheduler is to dynamically adapt to whatever the fab conditions are and optimally direct WIP throughout the fab to maintain linearity and optimize overall KPIs. Unfortunately, traditional rules-based scheduling solutions struggle to do that, and as a result, fabs today still look like this heat map. This is why a more advanced scheduler is needed. Now, I'm going to just zoom in on a few of the bottleneck toolsets so we can examine their behavior in more detail. Remember, the red represents when these toolsets have a lot of WIP queuing in front of them, and the green when the tools are not busy. What you can see is that none of these bottleneck toolsets are consistently a bottleneck. The bottleneck of the fab on any given day could be different to the last. This is why we've designed our global fab optimization. Using the power of cloud computing, we can optimize the flow of WIP across the whole fab every 5 minutes. Because we can solve this problem so quickly, the scheduler can dynamically react to any of the changes within the fab. For example, if a tool goes down and immediately we can redirect WIP to create the right balance across all the tool sets. The global fab optimization It's about ensuring the correct supply of WIP arrives at each toolset. But once the WIP does arrive, our toolset scheduler optimizes specific KPIs of that toolset. The toolset scheduler incorporates all of the physical constraints and allocates specific lots to specific tools. Now, in the next section, Tina from Seagate is going to speak to you about their experience of working with Flexiton and specifically talk about the application of the toolset scheduler at the photolithography tools at Seagate.
Thank you, Jamie. My name is Tina O'Donnell, and I'm the Global Wafer Systems Manager here at Seagate. And I have the responsibility of both our facility here in Derry in Northern Ireland and our Minnesota facility as well. So today I'll be discussing our experience with Flexiton in our photo areas. So firstly, Seagate wafer is a very complex process. We're a highly re-entrant factory. And what that means is that we're revisiting the same toolset multiple times throughout the process. We also have the complexity of being an R&D facility. Therefore, we need to ensure production shipments are met, and while we're reducing our cycle time for our R&D products. Our products today have approximately 1,600 unique steps, meaning that every single wafer must be processed 1,600 times through our process and metrology tools. And it takes about 69 months to manufacture a single wafer, depending on the product. As our tooling is expensive, utilizing our tools to their full capacity is extremely important to us, and we do whatever we can to, squeeze more out. So how are we set up today with Flexiton? So today we're fully integrated into the factory. So Seagate creates the data using Activity Manager and APF, and we transform and prep the data before we send it to Flexiton using web services. These data services then generate a digital twin of the fab, and they build all the dependencies between machines, lots, recipes, reticles, and tools and pods. The transition times between the steps are calculated, and we are updating the fab state continuously, meaning the position of the WIP, the state of the machines, and we send that to Flexiton. The Flexiton optimizer then uses mixed integer linear programming models and heuristics to solve the mathematical problem, as Jamie has mentioned earlier. The schedule output is returned then to Seagate using web services, and then we do a final validation of the model output before we fully integrate it into RTD. The dispatch and the reticle system then adjusts the optimal schedule to deal with any last-minute updates. And then the system provides a new schedule every 5 minutes to deal with the uncertain parameters such as transition times and processing times. And this is to deal really with, if a wafer arrives early or anything like that. So today we're going to focus on the photo tools. So let's look at the type of photo tools that we actually have in the factory today. So we really have 4 different types, as you can see here. And there is an extra level of complexity whenever we try to schedule around these tool sets. Now, photo and litho is really the true heartbeat of our factory, and it's so critical to ensure that we have an optimized schedule in this area. These tool sets are really high throughput, and we also have the added complexity of requiring reticles in order to process the WIP. We have 4 main types of tool sets, as you can see here. Some of these tools have a different number of pod load ports, A and B, whereas toolsets C and D have an internal reticle library. We also have 2 types of reticle storage, a reticle stocker and reticle cabinets, which present another set of challenges. The reticle stocker dispatches reticles in pods, which can only hold 6 reticles at a single time. And then these are then placed on a load port and either moved into the internal library of the tool, or else they remain on the load port on their pod. So what does all of this mean from a scheduling standpoint? It means that we need to look at the wafers that need to be scheduled, what reticles they use, what other reticles that we can combine with them into a single pod in order to utilize these tools to their highest degree. So we want to sort of focus on toolset D today, right? So this toolset has an internal library, and the reticles are stored in cabinets within the fab. We limit our process to a single reticle for each type. And what that means to us is that reticles will need to be moved between tools depending on the WIP levels and what enabled process paths we have. The other thing that we are a manual factory, as in we have manufacturing specialists that move reticles. So we also have to take that time into account and the variability with that. So Jamie is now going to talk about how Flexton tackle this complex problem.
As Tina mentioned, we're focusing now on the scheduling of a particular type of litho tool. Scheduling these tools is particularly difficult because there is only one reticle of each type available. If we want to run a particular recipe on a particular tool, we need to make sure that the reticle is placed in the tool. This is the perfect application of our toolset scheduler, which optimizes a specific toolset's KPIs whilst also respecting all of the constraints, in this case, the allocation of reticles. There are also a number of different conflicting objectives here. For example, you may want to decrease the cycle time at litho while simultaneously minimize the number of reticle moves. However, these two objectives can directly conflict with one another. In the toolset scheduler, we can tune the optimizer to appropriately treat those conflicting objectives. I'm now going to show you a few examples of that tuning. So we do the tuning by calculating how the toolset would perform if different weightings were put on the different objectives. Take the example on this slide. What you can see is a Gantt chart on the left, where each row represents a tool, and the colored boxes represent the lots allocated to each tool. The red arrows represent reticle moves that happen over the course of the schedule. This is a relatively simple example with only 48 wafers, which require 4 different reticles and are allocated across 6 available tools. In this schedule, we've told the optimization to heavily prioritize cycle time. Now, the resulting cumulative cycle time we get in the schedule is 18 hours in total. To get this short cycle time, we required 7 reticle moves. That's quite a lot of reticle moves to process such a small number of wafers. So we can adjust the objective weightings and quantify the impact. In this scenario, we're trying to strike more of a balance between cycle time and reticle moves. With this more balanced approach, we've reduced the reticle moves from 7 moves down to 5, but the trade-off is that we've added 1 extra hour of cumulative cycle time. So now we have 19 hours in total. And we can go even further. And now we've told the optimizer to make very few reticle moves. This, however, has had a very serious impact on cycle time. In this example, we've managed to reduce the number of reticle moves down from 7 moves down to 2, but the trade-off is that we've incurred an extra 5 hours of cumulative cycle time. Ultimately, how the optimizer deals with these trade-offs is up to the fab. When we deploy our scheduler, we work with the fab to tune the optimizer to deliver on the business objectives that you have in your specific fab.
Okay, thanks, Jamie. We need to schedule hundreds of reticles across the various tools. And, whenever we're focusing on toolset D in particular. As we have only 1 reticle of each type and used at any time, it may be scheduled across multiple tools. And as I said earlier, as this tool set is manual movement of reticles, we need a method to indicate to the manufacturing specialist what and when reticles should be moved from tool to tool or from cabinet into tool and vice versa. This is extremely valuable to the manufacturing specialist as they can make space and move reticles ahead of time instead of waiting until time of dispatch in order to go and move reticles. So Flexton have also provided this reticle removal ranking schedule. So what that allows us to do, it allows the manufacturing specialists to easily identify which reticles to move and what tools to make space in the internal library. This also gives them an indication of why things need to move. So we need to know when we need to move from tool A to tool B at a certain time because there's a wafer scheduled on that. And that's great with visibility for the manufacturing specialist. So let's talk about our results and our next steps. So whenever we do this, how does that translate into what the results that we're seeing in the factory today? So since deployment, you can see that we've increased our throughput, reduced our reticle moves, and reduced our queue time. So this is an amazing achievement. We're improving throughput and queue time while reducing the risk of reticle breakages. The other very important point here is that our manufacturing specialists give very positive feedback on the scheduling of this tool set. And in fairness, it has taken us time to get to this point. We did have the weights were slightly heavier on tool on throughput. And so therefore what that did is that had an impact then on our reticle moves. So we did a few iterations until we got that balance correct, you know, as Jamie mentioned earlier. So with the feedback from the manufacturing specialists, we have definitely improved our throughput, as you can see, and our reticle moves around this tool set. So the question is then, what about the other litho tools? So as I mentioned before, we have 3 other types of tools, as you can see here. These add an additional level of complexity, and because of the pod bills, and this has proven to be much more challenging. What we have done is on the on-tool testing of these tools have identified improvements in the optimization algorithm or internal processes within Seagate and the interaction of the manufacturing specials with the reticle stacker. So only for doing the on-tool testing have we discovered these. And again, it's an iterative process, so we get better and better at it each time we do trials. Now, this is, as I said, this has been complex and it has taken us a wee while to get here, but these tools are now in their final stages of testing before 24/7 deployment, which is due to happen now in this month. And our expectations on the improvement on these tool sets are even greater than toolset D. So in summary, this has been a huge change in Seagate to move from RTD to optimal scheduling for reticles and in addition to the wafer scheduling, especially for our manufacturing specialists. We've identified numerous hidden factory items, which has helped us improve our internal processes. And we see the benefits of local toolset optimization, showcasing a 10% improvement in throughput while still reducing the number of reticle moves, and queue time has been a great demonstration of the power of optimal schedule. Our next exciting step is to deploy the 24/7 on the remaining litho tools and measure those improvements. And then finally, the deployment of the global fab optimization is expected to provide benefits and a positive step change in cycle time and throughput KPIs. So I hope you find this presentation useful, and thank you very much for your time.
My name is David, and I'm the CEO and co-founder of Linteus. We provide a real-time process control solution for high-value manufacturing, and in particular semiconductor manufacturing. Today, I want to talk to you about our product and its underlying technology, and 2 specific use cases that we have developed and deployed in production. One around predicting physical characteristics of after deep trench etching process, and the second one around predicting the critical dimensions post-photolithography. So in both of those use cases, I'll come back to our methodology, some of the key results, and what is the value that we deliver and how it's being used today in the fab. Now, first, a few words about the problem we're tackling. We are seeing today that quality assurance and current quality assurance solutions are just not up to the task of real time. They are first sample-based, which means that they do not provide a comprehensive visibility over production. You only see when you can access quality results for a specific subset of production, and then you have to extrapolate to make sure that you have an idea of how your entire production is running. Second one, and most important one, it's actually after the fact. So when you think about fab operations, you're running wafers in an etcher or in any given machine, you then have to take them to the testing machine, queue, make sure the test is done properly, obtain the results, and only then take an action. During this whole time, the lot can be withheld, and you actually incur a significant what's called time to detect. So the time between the moment where a wafer is processed and the moment where its quality is known. We believe quality assurance should actually help spot defects immediately as they happen and be a tool for the process engineer to manage their process in real time. Lastly, it's rigid. So you define testing protocols once, and then you basically don't touch them, or if you're going to touch them, it's going to be a very long and complicated process. We think quality assurance here again should be adaptive and should be driving automation, should be driving flexibility and enabling process engineers to react rather than blocking them. Our experience in production is that switching to an exhaustive, real-time, and adaptive quality assurance can help reduce scrap by as much as 40 to 50%. Now, what's the product that's delivering this? You can think of Linserius as a virtual testing software that provides a real-time, actionable feedback on the quality of every wafer processed. Concretely, we are going to predict the result of quality test from the data that describes how the wafer is being processed. So FDC data that describe the conditions in the chamber, and tool data that tell us what has been the past utilization of the tool. Now, three main features in our product. First one, three main ways to create value. First one is real-time process control. As we've been saying, we enable process engineers to gain a real-time visibility over the quality of their production, which in turn means that if they detect a problem, they can actually react sooner and take an action sooner. It can be stopping the machine, calling for maintenance, or updating the parametering. This way, we are able to reduce time to detect by a very significant factor. Second use case, smart sampling. So here again, the current paradigm, if you want, in quality control is to randomly select units to test and to extrapolate the findings on those particular units to the entire lot. We believe sampling should be done intelligently. Since we return a prediction of a quality test for every wafer within the lot, we actually provide the opportunity to optimize metrology by selecting or identifying the wafers which have the highest probability of defect, which means that you can only send to metrology the wafers that really need to and where you're sure to catch a defect. Now, this helps optimize the number of testing steps or metrology testing steps, which in turn helps reduce cycle times and increase production throughput. And last one, automated diagnosis. We understood very clearly and very fast in our venture that if we are only to raise alerts without providing solutions, this is of limited interest and limited value to fab engineers. So we actually have the capability to identify with the input variables which ones have been deviating the most and can explain each one of our predictions, which means that in case of excursion, we have already pre-automated the data extraction and all of the correlation work that is necessary to identify the root cause. We help increase root cause identification time by as much as 70%, which beyond the obvious engineering time savings which are generated, help increase resolve issues faster and increase equipment uptime. Now, short note on the technology itself. Basically, what is driving us here is to deploy a solution which is as adapted as possible to the high demands of semiconductor manufacturing, which for us means being robust and secured. Secured is safe. We are hosting data. We can be hosting them, by the way, on-premise, on the customer premise, or on our clouds. So we have a zero trust policy and implement very strong security protocols around everything we do. The robustness is something that has declinations in different areas of the product. The most important one are around our predictive models. We want to make sure that our models are able to remain predictive for a longer period of time without retraining and are more scalable than anything on the market, which means that they should predict across several machines of the same type and several different product types as well. We have a process-centric modeling, so we believe different chemical or physical systems should be modeled in different ways. And one of the particularities of our approach, if you want, and I'll come back to this in more details in the use cases, is that we are combining material physics and AI to build the most robust models possible. We are leveraging physical documented relationships where they exist in order to optimize our use of customer data and decrease our dependency on the quality and the quantity of this data. Now, the software platform itself is a proprietary software platform that will host our models and perform a certain number of routine operations around them, from making sure they are fed with the right data at the right format to making sure the output of the model is also formatted in the right way and pushed to the right type of software on the customer side. And lastly, automate a number of retraining and monitoring operations. Now, rapidly, what we've been able to achieve so far, if I just had a few numbers to describe, we are in production in 2 fabs, deploying in 2 other fabs as we're speaking right now. And we have implemented this methodology across 6 of the most critical processes or process steps that you will find in a fab, namely deep trench, etch, and lithography, which I will come back to in further detail, but also STI etch, CMP, CVD, and ion implant. On Deep Trench Edge, what we've been able to demonstrate in terms of value, it's a 90% reduction in time to detect. So we basically provide a step change in the reactivity and in the lag with which engineers can monitor their process, and a 4x reduction in the sampling frequency after this particular process step. Here again, this has an immediate impact on cycle times. If you look further away in time, this could also have an impact on capital allocations to metrology equipment and floor space within the factory. It's important to note that this impact on both yield and cycle times is immediate. We pre-train our models before deploying them, and as soon as we switch on and you start taking production decisions, you actually immediately benefit from the real-time visibility that our product will provide, and you can start immediately reducing the sampling frequency that you are implementing in the fab. So this is not only a year one, but a day one ROI solution to provide, let's say, the lowest hanging fruit on both yield and cycle time improvement. Now, want to go back to our first use case around deep trench etching. So this is a use case one of the use cases that we have in production. A bit of context, for both of those use cases, we are working with a tier one automotive supplier in, let's say, mature fab, 200 millimeters, where quality is of utmost importance. This is important because we are deploying our models in the most demanding environments that you can find. We're talking about chips that need to last for around 15 to 20 years with heavy safety implications. So we are deploying AI in the same way as a physical measurement tool would be deployed. And this is very important for us and a very say, critical test of our robustness. The objective here was to predict the critical dimensions or the physical characteristics after deep trench etching process. You have the depth, the width, and the angle. I'm going to speak mostly about the angle, which is the most angle of the sidewall, which is the most critical characteristic in this instance. So first, quickly a recap of our modeling methodology. As we said, we have material physics expertise in the team who are taking care of step 1 and 2 of our modeling methodology. First one, selecting the variables. We want to make sure that we have an unbiased feature selection and that any potential failure that could happen within the machine is reflected in the selection of variables that we're going to give in input to the models. Here you can think about our methodology a bit like an FMEA that would perform directly on the tool to identify any potential failure mode, where this would be reflected in the data, and make sure that all of these important variables are selected, extracted, and fed into the model. This is a work that we do in close collaboration with the customer process engineers, obviously. Step 2, out of those variables, we need to build features that can provide or extract the most informative signal to the model. Again, here, our material physicists work in close collaboration with the customer and with the engineers to make sure our feature engineering makes sense. A very simple example of what we could do is we're working mostly with time series. And so sometimes the initial part, the first 5 seconds or the last 5 seconds of the time series actually do not make sense because the machine is ramping up or down. So they are not representative of anything happening to the wafer. And we want to make sure to exclude them in any type of feature that will be building out of this time series. So this is a simple example. We have more complex ones, but we actually go one step further into treating and analyzing the data that we receive. At this point, after step 1 and 2, we have an unbiased dataset, and we can go on the third step, which is really training our models. Here it's really classical data science or AI, I would say, training neural networks, finding the best architecture, optimizing hyperparameters to optimize performance. Here we have a set of proprietary techniques inspired from transferred and multitask learning domains, which help us, if you want, apply constraints in the training and make sure that our models are able to generalize in a better way than classically trained models. And then last but not least, we need to validate our results. So we are obviously keeping an unbiased section of the dataset that we receive that the model has never seen for performance testing, and we try to make sure that the conditions in which the model is tested are as close as possible to what you would find in production. So the idea is to provide a visibility over what would be the performance of the model in production through this kind of offline result validation. Now, going back to the results, we are evaluating the accuracy of our model in a very simple way. We compare the average error of our predictions, so the difference between the predicted value of the angle here and the actual value of the angle, with the actual control window for this process, so the physical variability tolerated by the customer. Our objective and what that we're complying for is to remain below 10% of the control window. So we are one order of magnitude lower than what is actually tolerated today by the customer. A second important point is to make sure that this performance is consistent for different types of angles. You have high angles, or top 25% of angles, for instance, medium ones, and the low ones, which are the bottom 25%. Obviously, you have very different quantities of data and examples that the models can learn from for those different segments of the dataset. So we want to make sure that the model is not, let's say, overfitting medium angles, but not performant on high and low angles. So we go one step further and check that it's consistent. We do have a better performance in the middle because we have more examples to learn from. What's important for us is that we stay in the same ballpark for both high and low angles. What you will see here on the right of the screen is how the existing dashboards and the existing process charts or flow charts from our customers are being populated with our predictions. It's very simple. It's exactly the same thing that what they are used to tracking, but fed in real time. And this is how they can really monitor their process and control their process in real time without changing their habits. So if you look at some of the conclusions that we can draw from this initial deployment and this initial kind of deep trench etching process, first thing, we only work with existing data. We only work with sensors which are already installed on the machine and data which is already centralized by the customer. In this example, in a 18 to 25-year-old fab, with this data, there is sufficient information to be predictive. Being predictive meaning achieving relative error of the absolute error, sorry, of the model, which is around 10% of the control window. Now, achieving this performance means that we're able to generate value from the first day of deployment through our kind of pre-training technique, both in the reduction in time to detect of 90% that we've seen already, and in the reduction in sampling frequency of around 4x. And lastly, no hardware, no capital expense is required to deploy this solution. As I said, we completely integrate on top of existing systems. We actually do not even plug into the machines themselves. We plug into the MES. So we are fetching data from the MES, running them in our models, and sending our contextualized predictions to the existing visualization or automation system so that the customer can access them and start managing their process in real time. Now I want to go back to our second use case around photolithography. Again, here, same type of problematic. We are in an automotive fab, quality is key. We have sample wafers where the CDs are measured post-photolithography, which is costing time, money, especially cycle time, and also comes with a lag. So it doesn't allow for, let's say, maximum reactivity and the maximum tighter control on the process. Here, what's interesting as well is that we have been working on predicting the mask CDs post-lithography. We have also worked on predicting the etch CDs and the final CDs. So we are able to deliver those gains at the scale of an entire module, photolithography plus etch, and are actually working now on integrating those two models together so as to predict directly the etch CDs. Here, I just want to present a bit let's say, the output of our variable selection work that I mentioned earlier in the deep trench etching process. So this is a very synthetic, let's say, vision of what our material physicists come up with when they work with engineers on the customer side. For a lithography process, we've made sure that we include all of the important variables, the most important of which being the previous etching results. So we had incoming CDs that were a very important factor in the model, optical parameters throughout exposure dose, and any parameters that gave us indication on the alignment of the wafer and the alignment of the beam as well, trying to understand what were the coordinates, the radius, and the rotation of the wafer in the machine itself. The way we came to this list of variables is actually quite interesting. We first read the manual of the machine. We make sure we understand exactly how the internal system of the machine is working, and we establish a first list of variables before even looking at the data given by our customers. This list of variables is then validated by process engineers who fill in the gaps and make sure that we get the data. They actually take care of sending us data for each of the variables that has been identified. So it's completely unbiased. Now, in terms of accuracy, here again, very robust results. So what you would see on the top chart is basically the benchmark between the real CD value in blue and the predicted CD value in red. So we are good in the middle. We are also able to catch, let's say, the more extreme CD values at the very high end and bottom end of the data set. And what's important, so on average, our accuracy is below 6 nanometers. It's even around 3 to 4 on average and always below 6. What's important to note as well is that this MAE is very stable over time. So what you're seeing on the bottom chart is actually how this MAE evolves per machine or per tool over time. And you can see that the standard deviation of this MAE over a period of almost 4 months stays below 0.9 nanometer. So we have demonstrated here a tolerance for the dynamic conditions that you would see in production. What this means concretely is that we do not have to retrain our model for at least a few months. Now, obviously, this is something that will not translate immediately in production. Our customer will not stop doing metrology for a few months, and their operational constraints and their obligations with regard to their own customers mean that they would still continue to measure at least once per day per critical technology. But still, implementing this change in sampling frequency would represent an 80% reduction in the measurements provided compared to what they do today. And this would be with a bi-weekly retraining of the model, so always staying with the most, learning from the most up-to-date data. The way this is being used beyond reducing the sampling frequency is also to speed up incident detection and avoid a lot of unnecessary reworks of the wafer. We are now implementing this on the etch section as well, where we will actually avoid not rework, scrap, with even greater value. Now, to conclude, I want you to get away from this presentation with two most important remarks, I would say. First thing is that there are significant gains that can be made across the entire manufacturing process in existing fabs, in legacy fabs. From reduced engineering time, increased yield, and reduced cycle time, our models are able to deliver those performance with the data which is already being collected, sitting on top of existing infrastructure. And so there are still gains to be made on those already depreciated fabs, which are or the more, let's say, captive because they do not have endless expansion capabilities. So that's really one of the lowest hanging fruit and one of the most powerful parts of our product today. Second one, and a bit related to the first one, the infrastructure to deploy the solution like ours actually already exists. And we have validated in multiple fabs that the data being collected, the IT infrastructure, and even the reaction and the quality control processes are fit for the deployment and for integration with our solution. So we really have a way to start delivering yield and capacity increases right now from day one ROI perspective in existing legacy fab, which are also the most demanding ones. Thank you very much for taking the time to listen to me today, and I'm now happy to take any questions that you may have.